Very much. Thank you all for coming. So it's about 10 years, almost exactly December 2004, that Dahi Stone, Miles Allen and I published a paper looking at the European heatwave of 2003. And this was the first example of this type of attribution study, as Heidi has introduced you to, which is looking at a specific climatic event, the extreme European heatwave of 2003, and making an attribution statement, making an explicit link between human influence and climate and that event. So 10 years have elapsed since then, and what my colleagues at the Met Office, Gareth Jones and Nikos Christidis, have done is to revisit that study. It's a paper we published last week in Nature Climate Change to see what 10 years of more data has told us in the meantime about the conclusions that we made 10 years ago in terms of the context of European summer temperatures. So just a little bit of background about the 2003 European heatwave. It was, as we said in the abstract of the paper back in 2004, it's probably the warmest summer since at least 1500. And of course it was, and this is a satellite picture showing you some of the temperature anomalies in that year. So some very extreme temperature anomalies centred around large parts of Central Europe there, you can see. And this had severe consequences, particularly for vulnerable elderly populations, estimates of many tens of thousands of excess deaths as a result of that. And I think that was also probably a bit of a wake-up call for authorities in Europe, because it demonstrated the vulnerability of those populations to extremes of that kind. So I'm sure lessons were learned from that. So if we look at the figure that we've figured in that paper, the 2004 paper, what we're looking at here in black are, so the black lines are the observed temperatures over this region in Europe, which is shown up here for summer temperatures. And the star there in 2003 is the anomaly relative to 1961 to 1990, a 2.3 degrees Celsius anomaly. Certainly an unprecedented in those records, and also very substantially warmer than the previous warmest year. The region that we'd chosen was not one that we selected, and there's quite a bit of discussion in the field around trying to avoid selection effects. And we talked about this in the paper, but the region that we chose was one that was already selected. It's one of those regions that Filippo Giorgio described in terms of looking at subcontinental regions, the so-called Georgi regions. We deliberately chose a region that was already existing. So you can see there where the highest temperature anomalies of 3 and 4 degrees relative to the 1961-1990 average are centred. So this was a very extreme season. And also on here we've got climate models of the day. This was the HADCM3 climate model, showing you, in the colours, showing you the HADCM3 climate model simulations of European temperatures going back in time to 1900 and then going forward into the future according to one of these sort of business as usual scenarios, assuming continuing emissions of greenhouse gases. And so when you put this information together, you can see that both how unprecedented this was in terms of the past record, but also if we're looking into the future, then there is clearly an increasing likelihood of such warm temperatures as we go into the future. There's clearly plenty of year-to-year variability, but also you can see how the warming trend is potentially projecting onto the likelihood of these types of extremes. Just also as a quick aside, you'll see that in Europe there wasn't a uniform warming. There was a flattening, even a cooling of temperatures in the 1960s and 70s, and at least in the HADCM3 model this was very well simulated and was a result of tropospheric aerosols cooling European climate during this period, at least in the model simulations. So we came to this conclusion which said that human influence is very likely at least doubled the likelihood of such an event. We're using IPCC calibrated language there. We said that there was a greater than 90% confidence in our statement about that. So we had come to the first example really of this type of event attribution statement. And I'll say a little bit more about this as we go along, about how we derive that conclusion. So this followed on from Miles Allen, who proposed this framing in 2003, actually before this was published in Nature in early 2003, so before the heat wave. And he pointed out that while at that point it may have been assumed that it really wasn't possible to link individual weather and climate events and make attribution statements attributing them to anthropogenic climate change. Well, actually, of course, well, maybe it seems obvious now, but Miles pointed this out first, was that climate change potentially is changing the likelihood of these and could be changing them quite significantly, as you saw in the previous plot. And therefore, we can make these types of attribution statements if we think about the likelihood of the event. Has the risk of such events increased or perhaps even decreased as a result of anthropogenic climate change? And in that paper of Miles back in early 2003, he produced a schematic. So this was not based on real data. This was based on a imaginary schematic of what such an analysis might come up with, and he came up with this idea of fraction attributable risk. And so what you're looking at here is a schematic of what such a calculation might look like. On the bottom x-axis, you're going from 0 to 1, and on the top, you're going in terms of the increase of the likelihood of such an event. So you've got 2 times and 4 times and 10 times, and that maps onto fraction attributable risk of respectively, if you're talking about 2 times a half, or if you're talking about 4 times 0.75. So what does that mean? That means that if you think of the analogy of, say, the loaded dice and getting a 6, where you've loaded the dice to make 6s twice as likely, that would be saying that the chances of getting 6 have doubled, and your fraction attributable risk then would be a half. And in that sense, you would say, well, a half of the times you get a 6, that's just bad luck or good luck. And the other half of the times, it's because the dice has been loaded. Or in terms of our extreme temperatures, it's because anthropogenic climate change is potentially changing the risk of such events. And likewise, if you're thinking about 4 times, then what you're saying is that 3/4 of the times that you come up with a 6, then that's attributable to the increased loading of risk as a result of that factor. So what we did in our paper back in 2004 is we produced the actual calculation of this for this event. So this is now not the schematic, this is our calculation at the time of that event. And we see exactly the same axis here, 0 to 1 and 2, 4 times and so on. The reason there's a distribution here is because of our scientific uncertainty in this estimate. If we had perfect knowledge, if we had no scientific uncertainty, we'd come to one number. But because of the calculation, the observational uncertainties, the modelling uncertainties, there is some uncertainty in that factor. And so what we saw here is that we were very confident at a very likely level that there was more than a half, there was more than a doubling of the probability. Our best estimate was actually something like 4 times. So the question is, what has happened since, and what is our reanalysis of that calculation now 10 years on? And so now this is taken from the paper that we published in Nature Climate Change last week. And what we're looking at now in red are the observations for the same region. We have updated observational records, and we also have updated models now, but we're looking at the same region. You can see 2003 there. You can also see that 2012 in this region was approximately as warm as 2003. So despite the fact that this was so unprecedented and substantially warmer than the previous record at that time, then you can see that that has been approximately equalled since. And you can also see on this plot, you can see the simulations in blue, and these are the CMIP5 models that include just natural forcing, so solar variability, volcanic eruptions, and of course the natural internal climate variability of the climate system, and so on. You can see that the observations are outside the spread of the model simulations there. And so what we do when we make this type of attribution analysis is we compare the world that we actually have, which includes both anthropogenic and natural forcings, as simulated in the model world in the top diagram here, where you can see the red distribution of the CMIP5 models, including both anthropogenic and natural factors. And then in the bottom plot is the plot we've already seen, which is the same observations with the natural models, the naturally forced CMIP5 models on the bottom there. And what we did in the 2004 paper, what we repeated in this latest analysis, was to make a calculation in which we calculated the chances, the odds of exceeding these warm temperatures in this red world, the world that we actually have, with the world that might have been had we not changed the climate. A quick aside here is that we don't just take the models as truth, we do an optimal detection regression analysis on those data to calibrate the models in terms of if they have over or underestimated the overall response to forcings, both natural and anthropogenic. And in that way, we can then calculate the odds of exceeding the temperatures. And what I've done here, what we did here in the paper, is we plotted it in this way. And what you've got here is two distributions. You've got a blue distribution, which is the possible range of temperatures in this European region in the world that we might have had we not changed the climate. You can see that there is quite a range of variability from year to year of European temperatures. But you can see that that range of variability has shifted as a result of the warming to this red distribution, and you can see where the 2003 heat wave lies. Now, this calculation is based on the situation as we had it back in 2003. So this is based on where we had estimated the anthropogenic signal had taken us to in terms of attributable warming, and you can see that there is shifting, and you can see how really very substantially unlikely such a heat wave was, even actually in the world that we currently had as our best estimate of how it has changed. Now, this is where we have now moved to as a result of just over a decade's worth of further warming, further climate change. So the blue distribution, so we've recalculated this now with data up to the present, and the blue distribution has not changed really. So that's similar to pretty much exactly what we had before. That's our natural distribution. But our red distribution, the world has now moved on, we have warmed up, and therefore the chances of exceeding such temperatures has increased. And we calculate that depending which thresholds you look at, that likelihood has increased by a factor of about 10. So events that were happening about twice a century are now happening about just back when we calculated in the early part of the 21st century are now happening about twice a decade. And indeed, very, very empirically and simplistically, if you like, that maps onto the fact that we have seen two occurrences now in that particular region of those types of temperature extremes. Then we also looked ahead into the future, and we can see, according to the different scenarios, the RCP scenarios looked at in the IPCC report, whatever happens, regardless of emissions, then it looks like by the 2030s and 2040s, such temperatures become regular events. But then in terms of the future, it depends very much in terms of the emissions as to whether we're in this world where we're sitting, the 2003 is sitting in the middle of that distribution, or whether we're in this world where the 2003 is sitting very much at the bottom end of that distribution. So just quickly to sum up, we have looked again at the analysis that we made 10 years ago. We've seen large increases in the risk of such heat waves as a result merely of about just over a decade's worth of further climate change. And we've also seen that the predictions that we made back then in terms of the likely future trajectory of European temperatures have been borne out by reality. So there's a basic verification we've seen in the observations of the calculation that we made back in 2004. So thank you for your attention, and I think we've got a bit of time for questions.
Yep. There's a microphone up front, but if you can speak loudly enough, then perhaps everyone can hear you.
Yeah. Was there any difference in mortality between the heat waves of 2003 and 12?
Well, that's a good question. I must admit, I'm not so this is I think the next step in some of these studies is to look through into the impacts. I think there was some important differences between those heat waves, and also the other point I think is that lessons were learned from 2003 as well. So I think it will be interesting to look and take these analyses through into the impacts in the way that you suggest, and it will be interesting to look also at the potential adaptation responses that have been achieved.
Yeah, we've got time for one more question.
So, interesting talk. So the statistics, of course, depends on how you define the heat wave in your series. And what can you tell us what you specifically did, like what was the region and the time period you used?
Right, sure, yes, thank you, and thank you for being able to clarify that. So we looked at European seasonal temperatures over that so-called Georgie region, which includes large parts of central France, Germany, and into Eastern Europe, and also includes the Mediterranean region. That has the advantage that we carefully verified the model statistics back in 2004, and the HADCM3 model has a very good representation of the variability on that region, and also, as you saw, the changes, and we did likewise a similar analysis for the CMIT5 models. Further work, and there's been a very interesting poster session I've just been to this afternoon, looking more in terms of some of these regime statistics and so on and so forth, looking down at the actual heat wave characteristics that led to the mortality would mean that we would need to extend these analyses to look at shorter period and shorter space type of of events, and I think that would be an interesting type of study to carry out.
Thank you very much.